In previous lecture, we saw that by choosing finer and finer meshes of points in a metric space, we can create a graph where edges are according to what balls of scale n intersect with other balls of scale n, or maybe n plus minus 1. In this video, we see some concrete examples of this construction. Remember that the goal will be to identify our original space as boundary of this graph in an appropriate sense later.
Let's take x again to be a singleton. A0 is just A1, A2, and all of them have to be just x. Okay, and then the graph will be, you have x0 and 0, first level root, then you have x0 and 1, and then you have x0 and 2, and you keep going down. Then these are neighbors because we said the vertical sets are there. Also, you can see that ball of x0 alpha to minus n intersected with ball of x0 alpha to minus n plus 1 is non-empty because x0 is in there. So this will be an edge, 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 and it will keep going up to infinity. And the distance is Euclidean distance, because if you are here and here, the shortest path is just length of this, which is isometric copy of 0, 1, and that and that. The hyperbolic graph, hyperbolic filling of the singleton with this distance is just, which means isometric. Up in metric world, this is indistinguishable to 0 to infinity with a usual Euclidean distance. You see that even a singleton does produce something interesting. And later we will see how to realize our original space, which is just the singleton, as the boundary of this. And the boundary, remember, this is not on the boundary of this space. This space is a complete space. It has no boundary. Remember, here and here, this is just an artifact of me writing on a piece of paper. It seems like we are in R2. No, this space in itself is an intrinsic object, and if you take Cauchy sequences, the limit is in the space. So it has no boundary per se, but we will be able to realize this, which is x itself, as boundary of the hyperbolic filling. So we will find a way to capture this one point as the boundary of this space. So we'll bring this infinity kind of closer and then say this infinity is the limit or the boundary of this graph G, and it is a copy of the original space you started with. How about multiple points? How about x being a bunch of points? Let's denote them by P0, P1, and Pn. Then, depending on their distances and on alpha, so let's say A0 is just P0, and then A1 could be just P0, or could be all of x, or could be some of the points. A2 will grow again, maybe for some time you don't grow, but definitely in finite time we will hit a, say, n0 equal to all of your space, and from that on, of course, everything else will be all of your space, n0 plus 2, and so on. So originally you start with 1 point. You always start with 1 point. That's the reason actually we scale the metric to diameter strictly less than 1. So P0, 0, the root is here. Our next one, again, it could be just one, or it could be multiple of them, or it could be all of them already. So my picture isn't representative. So 4 points here is just some points. And then you may add new points at some point. But very soon, there exists a level, there exists a 3. At some 3, maybe not 3, but 300, you will capture all of your space. So you will have, say, here, here. And then from that point on, you just repeat. And then you repeat. Okay. And then you repeat. Please bear with me for drawing many copies because they will be important. So first root is connected to everyone, and these might be connected or may not be connected. Also, I am kind of again restricted by my drawing on the plane. Maybe these two are connected, so I have to draw an edge independent of not intersecting the other edges. So suppose for now we have this, and then remember vertical lines are there, and let's say this relation is kept. This is also a new relation. This is there. Maybe this is also here. This relation is kept. Maybe both of these I meant. And then you go down. Okay. You can even have like this connected here. Let's also do it here. Okay, and here you can have many various horizontal relations, horizontal edges. But my claim is that after some point, there will be no horizontal edges. So, claim, let me write it here. There exists a knot so that there are no horizontal edges at levels n for n bigger than or equal n0. Okay, why? Because there exists n0 such that alpha to minus n0 is less than even, say, 1/2 of minimum distances of pi, pj. Of course, I not equal to j. Okay, and at that point, if you take and I have to put also tau here. So how did we define horizontal edges? We would say that the radius, so here is level n0. To be a horizontal edge, you will take a ball of radius alpha, tau times alpha to the negative. So tau times, sorry about that. So you want to draw a ball of radius tau, alpha to minus n naught. And then you want to take a ball around here of tau alpha to minus n naught. But because these distances are really small, maybe 2 isn't enough or something. Or wait, no, actually it works. So if they intersected, the distance of these two will be less than 2 tau alpha to minus n naught, but the distances are bigger. The minimum distance is bigger. So therefore they wouldn't intersect. So these two balls intersected with the other one will be empty, so there will be no edge. And then if you go to next level, of course, things are even worse for having a neighbor, because this same balls, now you have to have a shorter balls that meet, which then definitely, again, they won't intersect. So after some point, there will be no horizontal edges, and we have seen that the vertical edges are always there, so it will be all vertical edges from that point on forever. Okay, and then again, same. Okay, so I'm going into details of these examples because I will bring them back up later for many reasons. So here, possibly there are some horizontal edges, but at some point they will die down. Okay, so in this case, for instance, you can see that when you go further down, the distance between these two will go towards infinity, because you have to travel all the way to level before and not to be able to connect with the path. So their distances will be infinity, and that is why with this one-dimensional case, I already mentioned that we want to bring this infinity back to finite. So we want to play with this distances so that this whole becomes something bounded, so that we can talk about its boundary. We'll do similar changes here so that this apparently infinite distance between these guys does turn into something finite as n goes to infinity. And from those, we will in fact recover our original space, which is where is my P0? So maybe P0 is here. So we will cover P0 and all the other ones. And the distances between them in the original metric space, d of x, in the original metric space, we will see that this will be by Lipschitz equivalent with the right choices of parameter to, actually no, with any parameters alpha and tau, this will be by Lipschitz to the metric that we put on the boundary of the graph. So this is my graph. Let me add these so there is no confusion here. So there will be this graph. And as I said, by playing with the distance function, we will turn it into kind of a finite diameter graph, and then we will, these limits of these edges, the ends, will constitute the boundary of the graph. And we will see that by choosing that metric, by constructing that metric the right way, the distance on the boundary of the graph of these pi pj's will be by Lipschitz comparable to the original distance that they had in the original metric space x, which lies here. So x will be equal up to by Lipschitz to the boundary of graph. That's the whole business and idea behind hyperbolic filling, that we start with x, we build a graph which is kind of nice, connected, lots of path and stuff, and we realize our original space as the boundary of this this object. Okay, so as an exercise or a follow-up, I will ask you to see how the behavior on the line segment goes. So exercise, draw hyperbolic graph with, say, alpha equal 2. And maybe what do path look like? What do path or shortest path in the, which are for the distance, look like in the graph GD. Okay, I'm not sure how long this video became, but because it was full of examples, maybe you will forgive me for that. See you in next video, where we begin the more serious business of talking about a more delicate geometry of this graph, and hopefully begin to talk about how do we construct a new distance on the graph to tame it a bit. Thanks for watching, and please give me thumbs up and comments if you have, to let me know that the content is something you like.